Our next person is going to be Ben Liu, and he's going to tell us about his project, which was a novel printing technique of 3D inverse opals from freestanding crystalline structures for next-generation optical sensing. And his mentors were Mr. Alvin Tan, as well as Miss Cecile Chazot. And yeah, we can clap while he gets his mic on.
So throughout history, natural materials have been large inspirations for material design and catalysts in medical applications. And in nature, there are prevalent examples of organisms controlling structure and function over large and precise scales in the form of photonic crystals in chameleons and strong elastic fibers in silk. And recently, synthetic design has moved toward a trend of replicating these unique optical, chemical, and mechanical properties through engineering 3D lattice structures and incorporating natural materials themselves. And as seen in nature, crystalline structures are composed of multiple layers of symmetrical organized patterns of colloids, which are nanoscale particles. And inverse opal structures are very similar. However, instead of these particles in these spheres, you have open air in these spaces forming like a nanoporous structure, as seen in this image. And these structures are under intense research because of their extraordinary applications in optical photonic sensing, chemical doping applications in drug release platforms, mechanical strength, and biological tissue regeneration. And there are two current techniques in 3D printing that we must first understand to grasp our problem. So the first is evaporative self-assembly, which basically assembles individual layers of crystalline colloids on a heated substrate surface, and then they're subsequently stacked on top of each other to form these microstructures. And although we're able to form these crystalline microstructures, they're limited to 2D planar designs and are therefore impractical on a 3D functional scale. And the second method of 3D printing is direct writing, which basically uses a control nozzle to etch these 3D designs to create these large-scale freestanding structures that you're more familiar with. And this method doesn't concern the formation of crystalline structures and therefore overlooks many of the properties that we're interested in. So recently, a team of researchers at MIT invented a new form of assembly known as direct write freeform. And basically what it does is it combines evaporative self-assembly and direct writing, in which a colloidal solution is dispensed from a needle tip onto a heated substrate surface, forming this liquid bridge. And then you have these colloidal particles that are flowing through this liquid bridge and assembling into organized crystalline layers on top of each other through evaporative heating. And then we have a lowering stage mechanism that is able to build the structure up as the needle stays in its constant position. And on the right over here, we have a real-life photograph of this process. And we use this method throughout our study to create these 3D templates. So this diagram shows the 5-step process that we use in creating these model inverse opal structures. And the previous method that I described before completes the first step of structure assembly. However, there are 4 other steps that we have to characterize and study and tailor to intermediate printing techniques in order to create these model inverse opal structures. So we originally take the crystalline template, we then infiltrate it with a soap water solution to etch in all the gaps and the interstices before we cross-link the structure to strengthen the silk. And then we etch away the original colloids in the crystalline structure to form this nanoporous-like material. And then we finally dope the structure in order to functionalize it. And so this brings us to our problem and basically our target properties within our research. So we initially want to assemble freestanding crystalline structures using the method that I described before. And we want to tailor these assembly factors to optimize infiltration and therefore the formation of these inverse opal structures. And then in our inverse opal structures, we want to promote homogeneous distribution of these features across the entire structure, the crystalline arrangements that I talked about before, and also the retaining of the 3D template that we're given. So we're going to solve this and achieve our goals through a 2-layer process flow. And in the first layer, we're going to analyze individual factors listed here in each of the 5-step processes. And basically, what we're going to try to do is we're going to study these individual factors by microscopically analyzing each of the stages in the etching process and looking for crystalline defects and target features. And after we can understand how these factors relate to the creation of these structures on a general scale, we can tailor that understanding to our second layer, which is the creation of these techniques in order to enhance infiltration and cross-linking. And then after we establish these optimal parameters in these techniques, we can take them to create our optimized structures and functionalize them to demonstrate their applicational viability. And then we can And we'll be referring to this diagram later as a roadmap to see the big picture. So we first studied assembly results, and we studied two main factors, particle type and particle diameter. And so in this image table over here, we're comparing PMMA structures and polystyrene structures, which are very common particle types used in these studies. And we compare photos before etching, after etching, and an SEM of surface features to look for the crystalline properties. And what we see is that the main conclusions we can draw are that the polystyrene structures retain their structure significantly better as compared to the PMMA and display the target inverse opal features. And we also extended a similar experimental design to studying particle diameter and reached similar conclusions in favor of larger particle diameters and specifically 500 nanometer particles. And next, we looked at infiltration factors, so silk concentration and infiltration time. And in this image table, we look at the etching images of the structures and the SEM images at 3 different concentrations. So some of the main observations that we can make are that in the 1% structure, the top region was completely etched away, and it was unraveled in the 3.6% structure and well retained in the 7% structure. And when we look at the SEM images, we can see the formation of a silk skin in the 1% structure, which is indicative of insufficient infiltration. And we can see the model inverse opal features that we want in the higher concentration structures. And again, we extended this experimental design to studying infiltration time and saw that longer times favored better structural retention and these inverse opal features that we're looking for. So returning back to our roadmap that we just showed, we've completed first our characterization, and I've showed you the process in which we've analyzed these main factors, and we have a general understanding of how they work on a 3D scale. And so now we can tailor those to developing methods to enhance infiltration and cross-linking through these methods, and now we're going to move on to that. So we originally developed the vacuum infiltration strategy based on the original hypothesis that the reason we weren't achieving full infiltration and homogeneous distribution of these features was that there's air trapped between colloidal particles and within the structure. And so we hypothesized that if we use the vacuum, we could remove this air and therefore promote more uniform infiltration. And so in this image table, we compare samples with the vacuum and without the vacuum, and we see different levels of magnification in the SEM. So we see that both samples have pretty good structural retention. In these images, we see homogeneous distributions of inverse opals with the technique, and we see the formation of a silk skin on like the bottom region without the vacuum technique, and we see good inverse opal features in the high SEM images. And moving on to our second technique, we developed a novel methanol vapor technique because one of the major problems that we faced in our research was that when we submerged our structures in methanol solution to cross-link the structure, which is a common technique cited in previous studies, the structure would degrade and the silk frame would collapse, as seen here. And so we wanted to develop an approach that could homogeneously cross-link the structure, but also retain and provide the minimal physical disturbance to the structural frame. And so we did this by infiltrating within vacuum with methanol vapor, and we saw that we achieved really good structural retention compared to submerging in the methanol solution and our target inverse opal features and SEM. So now we can kind of discuss our first and second layers. And if we have time in the Q&A session, we can get into detailed discussions on kind of possible explanations to why we're seeing the results. But so far, we've been able to study 4 major factors and come up with optimal parameters to functionalize our structures. And then we've looked at 2 novel techniques that we've developed in order to enhance infiltration and retention of the structure, as well as cross-linking. And these techniques can be applied to basic material science research in studying infiltration in model 3D systems and also cross-linking fragile materials. And so now we applied these optimal parameters and these techniques to creating our functionalized and optimal structures. So originally we created the 500 micrometer structures, and we looked at different levels of the magnification in the SEM. So we saw pretty good structural retention and homogeneous distribution of inverse opal features. And then when we looked at the high SEM, we saw the crystallinity in these features, which were our target properties. And then we looked at 80 micrometer structures that basically, our hypothesis was that if we applied these parameters to thinner structures, we might actually achieve full infiltration because they're thinner. And so we were able to achieve full infiltration with our other target properties, such as crystallinity and homogeneous distributions. So we took these structures and we functionalized them to try to demonstrate applicational viability in real-world applications. So we did this by doping them in quantum dots, which are materials used for fluorescent tagging. And they display this fluorescent quenching mechanism in which you can detect particles and metals, in this case metal cations, through the changes in fluorescence. And so this is the original sample after doping, so before exposure to copper chloride, which was what we're trying to detect. This is after exposure to 50 micromolar copper chloride, so you can see the structure getting significantly dimmer. And this is just above the threshold for toxicity in copper. And then you see the structure getting a little bit dimmer after addition of an additional concentration. So now we can go to our conclusion. What we've done throughout the study is we've created a novel printing technique for creating 3D inverse opal structures. And through this, we've studied a lot of different factors involved in infiltration. And we've come up with general understandings of how these factors relate on a big scale and structural retention and mapping of these features on 3D scales that haven't been done before. And then we've been able to, in between, develop intermediate printing techniques to enhance cross-linking and enhancement methods that can be applied to other studies in material science. And then we've been able to apply these to develop fully infiltrated homogeneous inverse opal structures, as well as a copper chloride sensor that we can theoretically apply to detect toxicity levels in water. And then this is a method that can be applied to multiple fields. So in the introduction, I talked about how we can develop biosensors, drug release platforms, and laser development. And in previous studies, they've developed these in single layer and 2D layer microstructures. But now this study brings that to a step closer to actually putting these applications in the real world in the hands of humans like you and me. And so future directions will consist of testing some new factors that we can look at for better structural retention and better infiltration of the structure. And then we can look to perform more precise optimization. So far, we've scanned across and developed a framework to kind of understand the general properties and some intermediate printing techniques. And then we can try to achieve tunable porosity and actually precise engineering of these 3D lattice structures. And we can look into new applications in these 3D scales. When we studied these inverse opal features on 3D scales, we saw many results that differed from previous studies on 2D scales. And so we believe that we'll also see differences arrive in 3D applications. And we can use this printing method. Researchers in other fields can use this 3D printing method to study these applications and to put them into practice. And so some acknowledgements. I'd like to acknowledge CE, RSI, and MIT for giving me this wonderful opportunity. It's been a really amazing 6 weeks. My mentors, Alvin Tan, Cecile Chazut, and John Hart, they really encouraged me throughout this research and kind of guided me on experimental designs and things like that. Definitely my lab group, my tutor, Peter Liu, for helping me a lot on the paper and presentation. Dr. Amy Silman for doing such a great job with RSI and helping me find my mentor. All of my sponsors, especially my sponsor from DSHA, who's here today, and a couple special people, including the last week TAs, and some people who helped me read my paper and give me support throughout RSI. Daniel Michael, who's my counselor, and just supported me throughout the entire process and read through a lot of things and taught me a lot about life. And, and Ann Lee for giving me so much help on the presentation and always believing in me. Thank you. Oh, yeah.
Okay, any questions for Ben?
Yeah. So the question was, which parts did I do? So let's just jump back to the process flows. It's a lot clearer. So I arrived at a pretty good time in my lab. Our lab basically just finished developing direct write freeform, which basically allows us to assemble 3D crystalline structures. And now they are trying to look to the next stage of developing these inverse opal features. So I arrived right at that time in which they just got that paper published with a new assembly form. So basically what I tried to do was look at literature and look at all the different factors that are involved in the 2D assembly. So the 5-step process is pretty basic for infiltrating and creating these nanopore structures. So my mentor and I kind of looked toward these factors, and I created most of the experimental designs toward testing these factors and actually keeping track of where we are in the testing and which experiments we would need to run. And then I came up with a novel methanol vapor cross-linking method. I basically just tried to study different pieces of literature and piece them together. And that was kind of the inspiration for the vacuum infiltration that my mentor recommended. And then the functionalization was a pretty relatively simple process, with just adding the quantum dots to our infiltration. So that was the idea of my mentor. Yeah.
Other questions? Yes.
How many experiments did you run approximately?
Right. So we created 30 total structures, around 25 to 30 total structures. And we can use one of those structures in each experiment. So it takes around 1 to 2 hours, around 1 hour and 40 minutes to create each of these structures through the assembly process and also the apparatus setup. So that was one of the limitations. And for each study in each of these factors, we tried to repeat each experiment around 3 different times with the 3 different parameters. So those were in the amount of experiments, I would say around 50 with like testing the functionalization and other properties.
Other questions? Yes, you moved, but it's the same person from over there, isn't it?
So you got your best results at the highest concentration you tested. Do you think it would get even better at higher concentrations?
Yeah, great question. So the question was, we got our best results at the highest concentration, and would the results improve with higher concentrations? Let's see. So this was using 7%, and the reason we stopped at 7%, and when we selected our parameters, we looked at first previous studies. So like 1% was used for these smaller microstructures. So that was our lowest parameter, and then for 7%, that was based on the physical properties of silk. So after, and like even at 7%, the viscosity of silk is relatively high. So that can kind of influence the infiltration process. We haven't studied that mechanism in detail, but relatively when we're manually infiltrating, it gets really hard after 7% because the solution's super viscous. So yeah.
I think we have time for one or two more questions. All right, that's okay too. We can always, oh, wait, what's up? Yeah. Oh, you were gonna clap. Well, okay, let's clap. Great work, Ben.